Now let's look at one of the motivations for using pure procedures. We'll write a simple main program that differentiates a function using central differences. As usual, we will prevent implicit typing. We'll declare two real arrays, give them the allocatable attribute, which obligates the compiler to deal with almost all of the memory management associated with these arrays, both in terms of allocating memory for them and deallocating them when they go out of scope. One will hold, let's say, temperature values. The next will hold its derivatives. Let's define a constant as a grid spacing. And we'll define a variable that we'll need for looping. Let's initialize the temperature array to have values, integer values that range from 0 to 10. Times dx. We're going to compute derivatives only on the points internal to the solution domain. So we'll allocate the temperature array ourselves, and it will have an index that ranges from the lower bound of the temperature array +1 to the upper bound of the temperature array index -1. Now, we don't care in what order these are accomplished, so we'd like to communicate to the compiler that there's an opportunity here for parallelism, and the type of parallelism that the compiler is likely to employ would be vectorization, or what's referred to as single instruction multiple data programming. But it's also possible that a compiler could use a different parallelization strategy, such as multi-threading. We're going to loop from the lower bound of our derivative array to its upper bound, but specify that those can happen in any order. And then to actually compute each approximation to the derivative, we're going to call a procedure. However, the language stipulates that in order to call a procedure inside a do concurrent construct, the procedure must be pure. Now let's just print the results. And let's implement the procedure as what Fortran would call an internal procedure. And we'll make it pure. We don't have any need to modify our arguments, so we'll give them intent in, which for pure functions is a requirement. And we're returning a scalar result for one grid point. And this is our central difference formula. And it's also worth noting that there are whole languages built around this idea of side effect-free, purely functional programming. And then we'll compile. With the Intel compiler, we have to tell it to conform to the standard, which requires the allocation of those arrays upon assignment. And we'll run it, and we can see the results. We have a linear distribution of temperature, so we get a constant derivative. This ability to declare a procedure as pure gives the compiler a lot of important information that it can use for optimization purposes. For example, the compiler knows that anytime the procedure receives the same argument, it returns the same result. Therefore, if it sees a call with the same argument more than once, it only has to do the calculation once. Also, there's the opportunity for vectorization or multi-threading, different forms of parallelization, as I mentioned. And in the case of the GNU Fortran compiler, this is sufficiently useful that the compiler will actually attempt to detect when a procedure can be pure, even if the programmer doesn't tell them. In the next section of this JOLT, we'll also see where writing pure procedures that we use to implement user-defined operators gives us not only a nice expressive syntax, but also a high level of parallel efficiency, because the pure procedures, since they don't modify their arguments, enable us to write code that is highly asynchronous. Synchronization can hurt parallel performance, and so the pure procedures are helping us to write better, higher performing parallel code.